So last time we were focusing on repeated interaction, and that's what we're going to continue with today. There's lots of things we could study under repeated interaction, but the emphasis we're going to of this week is can we achieve cooperation in business or personal relationships without contracts by use of the fact that these relationships go on over time. And our central intuition, where we already started from last time, was perhaps the future of a relationship can provide incentives for good behavior today. Right? Can provide incentives for people not to cheat. So specifically, let's think of an example, and we'll go back to where we were last time. Specifically, suppose I have a business relationship, an ongoing business relationship with Jake. And each period, I'm supposed to supply Jake with some inputs for his business, let's say some fruit. And each period, he's supposed to provide me with some input for my business, namely vegetables. All right? And clearly there are opportunities here in each period for us to cheat. We could cheat both on the quality of the fruit that I provide or the quantity of the fruit that I provide to Jake. And he can cheat on the quantity or quality of the vegetables that he provides to me. All right? And our central intuition is, perhaps what can work is, what can give us good incentives is the idea that if Jake cooperates today, then I might cooperate tomorrow. I might not cheat tomorrow. And conversely, if he cheats and provides me with lousy vegetables today, I'm going to provide him with lousy fruit tomorrow. Right? And similarly for me, if I provide Jake with lousy fruit today, he can provide me with lousy vegetables tomorrow. All right? So what do we need? We need the difference in the value of the promise of good behavior tomorrow and the threat of bad behavior tomorrow to outweigh the temptation to cheat today. Right? It's cheaper. I'm going to gain by providing him with the bad fruit or fewer fruit today, bad fruit because those I'd otherwise have to throw away. So that temptation to cheat has to be outweighed by the promise of getting good vegetables in the future from Jake, and vice versa. All right? So here's that idea on the board. What we need is the gain, if I cheat today, to be outweighed by the difference between the value of my relationship with Jake after cooperating and the value of my relationship with Jake after cheating tomorrow. All right? Now what we discovered last time, this was an idea I think we kind of knew. We've kind of known it since the first week. But we discovered last time, somewhat surprisingly, that life is not quite so simple. And in particular, what we discovered was we need these to be credible. So there's a problem here of credibility. So in particular, if we think of the value of the relationship after cooperating tomorrow as being a promise, and the value of the relationship after cheating as being a threat, we need these promises and threats to be credible. We need to actually believe that they're going to happen. And one very simple area where we saw that ran immediately into problems was if this repeated relationship, although repeated, had a known end. Right? And why did known ends cause problems for us? Because in the last period of the game, we know that whatever we promised to do, or whatever we threatened to do, in the last period, once we reach that last period, in that subgame, we're going to play a Nash equilibrium. What we do has to be consistent with our incentives in the last period. Right? So in particular, if there's only one Nash equilibrium in that last period, then we know that in that last period, that's what we're going to do. So if we look at the second to last period, we might hope that we could promise to cooperate if you cooperate today, tomorrow, or you could promise to punish tomorrow if you cheat today. But those threats won't be credible because we know that tomorrow you're just going to play whatever that Nash equilibrium is. Right? And that lack of credibility means there's no scope to provide incentives today for us to cooperate, and we saw things unravel backwards. All right? Right? So the way in which we ensure that we're really focusing on credible promises and credible threats here is by focusing on subgame perfect equilibrium, the idea that we introduced just before the Thanksgiving break. And we know that subgame perfect equilibria have the property that they have Nash behavior in every subgame, so in particular in the last period of the game and so on. All right? So what we want to be able to do here is try to find scope for cooperation in relationships without contracts, without side payments, by focusing on subgame perfect equilibria of these repeated games. And right at the end last time, we said, okay, let's move away from the setting where we know a game is going to end, and let's look at a game which continues, or at least might continue. So in particular, we looked at the problem of the prisoner's dilemma, which was repeated with the probability that we called delta each period, with the probability delta of continuing. All right, every period we're going to play prisoner's dilemma. However, with probability 1 minus delta, the game might just end every period. All right, and we already noticed last time some things about this. The first thing we noticed was that we can immediately get away from this unraveling argument. Because there's no known end to the game, we don't have to worry about that thread coming loose and unraveling all the way back. So at least there's some hope here to be able to establish credible promises and credible threats later on in the game that will induce good behavior earlier on in the game. All right, so that's where we were last time. And here is the prisoner's dilemma. We saw this last time. All right, and we actually focused on a particular strategy, but before I come back to the strategy that we focused on last time, let's just see some things that won't work, all right, just to reinforce the idea. So here's a possible strategy in the prisoner's dilemma. A possible strategy in the prisoner's dilemma would be cooperate now and go on cooperating regardless of what anyone does. Right, so just cooperate forever regardless of the history of the game. Now, if two players, if Jake and I are involved in this business relationship, which has the structure of a prisoner's dilemma, and both of us play this strategy of cooperate now and cooperate forever no matter what, clearly that will induce cooperation. That's the good news. The problem is that isn't an equilibrium. It's not even a Nash equilibrium, let alone a subgame perfect equilibrium. Why is it not a subgame perfect equilibrium? Because in particular, if Jake is smart, and he is, Jake will look at this equilibrium and say, Ben is going to cooperate no matter what I do, so I may as well cheat. And in fact, I may as well go on cheating. Right? So Jake has a very good deviation there, which is simply to cheat forever. Right? So the strategy, cooperate now and go on cooperating no matter what, doesn't contain incentives to support itself as an equilibrium. And we need to focus on strategies that contain subtle behavior that generates rewards and promises of rewards and threats of punishment that induce people to actually stick to that equilibrium behavior. All right, so everyone's clear that cooperating no matter what, it sounds good, but it isn't going to work. People aren't going to stick with that. So instead, what we focused on last time, and actually we had some players who seemed actually, they've moved now, but they seemed actually to be playing this strategy, we focused on what we called the Grim Trigger strategy. And the Grim Trigger strategy is what? It says, in the first period, cooperate, and then go on playing cooperate as long as nobody has ever defected, nobody has ever cheated. But if anybody ever plays D, anybody ever plays the defect strategy, then we just play D forever. All right? So this is a strategy. It tells us what to do at every possible information set. It also, if two players are playing the strategy, has the property that they will cooperate forever. That's good news. And what we left ourselves last time was checking that this actually is an equilibrium, or more generally, under what conditions is this actually an equilibrium. All right, we were halfway through that calculation last time. So what we need to do is we need to make sure that the temptation of cheating today is less than the value of the promise minus the value of the threat tomorrow. All right, we did parts of this already. Let's just do the easy parts. So the temptation today is if I cheat today, I get 3, whereas if I went on cooperating today, I get 2. So the temptation is just 1. All right? What's the threat? The threat is playing D forever. So this is actually the value of D, dd, forever. And I want to be careful about forever. When I say forever, I mean until the game ends, because eventually the game's going to end. But let's use the code forever to mean until the game ends. And what's the promise? The promise is the value of continuing incorporation, so the value of CC forever. All right, that's what this bracket is. That's what this bracket is, and it's still tomorrow. All right, so let's go on working on this. So the value of cooperating forever is actually, let's be a bit more detail, this is the value of getting 2 in every period. So it's the value of 2 forever. And this is the value of 0 forever. All right? Okay, so the value of 0 forever, that's pretty easy to work out. I'd get 0 tomorrow. I'd get 0 the day after tomorrow. I'd get 0 the day after the day after tomorrow. Or more accurately, I'd get 0 tomorrow. I'd get 0 the day after tomorrow if we're still playing. I'd get 0 the day after tomorrow if we're still playing, and so on. But that isn't a very hard calculation. This thing is going to equal 0. So this object here, let's use my other colored chalk. This object here is just 0. Is that right? This object here is 3 minus 2. I can do that one in my head. That's 1. All right? So what I'm left with is the value of getting 2 forever. And that requires a little bit more thought, but let's do that one bit of algebra because it's going to be useful throughout today. So this thing here, the value of 2 forever is what? Well, I'd get 2, that's tomorrow, and then assuming I'm still playing the day after tomorrow, so I need to discount it, with probability delta, I'm still playing the day after tomorrow, and I get 2 again. All right? And the day after tomorrow, I'm still playing with the probability that the probability that the game didn't end tomorrow or didn't end the next day, so that's with probability delta squared, and again I get 2. And then the day after, what is it? This is tomorrow, the day after tomorrow, the day after the day after tomorrow, this is the day after the day after the day after tomorrow, which is delta cubed 2, and so on. All right, everyone happy with that? All right, so starting from tomorrow, if we play CC forever, I'll get 2 tomorrow, 2 the day after tomorrow, 2 the day after the day after tomorrow, and so on. And I just need to take account of the fact that the game may end between tomorrow and the next day, the game may end between the day after tomorrow and the day after tomorrow, and so on. All right, everyone happy with that? All right, so what is the value, what is this thing? Let's call this x for a second. Right, so we've done this once before in the class, but let's do it again anyway. This is the value, this is the geometric sum. Some of you may even remember from high school how to do a geometric sum, but let's do it slowly. So to work out what x is, what I'm going to do is I'm going to multiply x by delta. All right? I'm going to multiply x by delta. All right, so what's delta x? So this 2 here will become a 2 delta, and this delta 2 here will become a delta squared 2, and this delta squared 2 will become a delta cubed 2, and this delta cubed 2 will become a delta to the 4 2, and so on. All right? And now what I'm going to do is I'm going to subtract the second of those lines from the first of those lines. All right? So what I'm going to do is I'm going to subtract x minus delta x. All right, so I'm going to subtract the second line from the first line, and when I do that, I'm going to notice, I hope, that this 2 delta is going to cancel with this 2 delta, and this delta squared 2 is going to cancel with this delta squared 2, and this delta cubed 2 is going to cancel with this delta cubed 2, and so on. All right, so what I'm going to get left with is what? Everything's going to cancel except for what? Except for that first 2 there. All right, so this is just equal to 2. All right, now this is a calculation I can do. So I've got x is equal to 2 divided by 1 minus delta. All right, so just to summarize the algebra, getting 2 forever, that means 2 plus delta 2 plus delta squared 2 plus delta cubed 2, etc. The value of that object is 2 over 1 minus delta. 2 over 1 minus delta. All right, so we can put that in here as well. This object here, 2 over 1 minus delta, is the value of 2 forever. All right. Now, before I go on to a new board, I want to do one other thing. All right. I've got on the left-hand side, I've got my temptation. That was 1. I've got the value of cooperating forever, that starting from tomorrow, which is 2 over 1 minus delta. And I've got the value of defecting forever, starting from tomorrow, which is 0. All right. However, all of these objects on the right-hand side, they start tomorrow. Whereas the temptation today is today. All right? Temptation today happens today. These differences in value start tomorrow. Right? Since they start tomorrow, I need to discount them because we don't know that tomorrow is going to happen. The world may end, or more importantly, the relationship may end between today and tomorrow. So how much do I have to weight them by? By delta. Right? I need to multiply all of these lines by delta, and so on. All right? Now this is now a mess, so let's go to a new board. All right? And let's summarize what we now have. Now what we're doing here is asking, is it the case that if people play the Grimm trigger strategy, that is in fact an equilibrium, that is a way of sustaining cooperation? And the answer is, we need 1, that's our temptation, to be less than, big bracket, 2 over 1 minus delta. That's the value of cooperating forever starting from tomorrow. Minus 0, that's the value of defecting forever starting tomorrow. And this whole thing is multiplied by delta because tomorrow may not happen. Okay, everyone happy with that so far? I'm just kind of collecting up the terms that we did slowly just now. All right, so now what I want to do is, the question mark here, because we don't know whether it is, I'm going to solve this for delta. All right, so when I solve this for delta, I'll probably get it wrong, but let's be careful. So this is equivalent to saying, don't have to worry about the zeros, this is equivalent for saying 1 minus delta is less than 2 delta. And it's also equivalent to saying, therefore, delta is greater than or equal to a third. Delta is greater than or equal to a third. Everyone happy with that? Let me just turn my own page. All right. So what have we shown so far? We've shown that if we're playing the Grimm trigger strategy and we want to deter people from doing what? From defecting from this strategy in the very first period, then we're okay provided delta is bigger than a third. But at this point, some of you could say, yeah, but that's just one of the possible ways I could defect from this from this strategy. After all, the defection we just considered, the move away from equilibrium we just considered was what? We considered my cheating today, right? But thereafter, I reverted back to doing what I was supposed to do. I went along with playing D thereafter. Right? So the particular defection we looked at just now was in period 1, I'm going to defect, right? But thereafter, I'm actually going to do what the equilibrium strategy tells me to do. I'm going to go along with the punishment. I'm going to go along with the punishment and play my part of DD forever. All right? So you might want to ask, why would I do that? Why would I go along? You know, I cheated the first time, but now I'm doing what the strategy tells me to do. It tells me to play D. You know, why am I going along with that? you could consider going away from the equilibrium by defecting, for example, in period 1, and then in period 2 do something completely different, like cooperating. All right? So we might want to worry, how about playing D now, and then C in the next period, and then D forever. Right? That's just some other way of defecting. So far we said I'm going to defect by playing D and then playing D forever. But now I'm saying let's play D now, well, then play a period of C, and then D forever. Right? Is that going to be a profitable deviation? Well, let's see what I'd get if I do that particular deviation. What play is that going to induce? Remember, the other player is playing equilibrium, so that play is going to induce, in the first period, I'm playing D and Jake's playing C. In the second period, Jake's going to start punishing me, so he's going to play D, and according to this deviation, I'm going to play C. So in the second period, I'll play C and Jake will play D. And in the third period and thereafter, we'll just play DD, DD, DDD. Right? So this is just some other deviation other than the one we looked at. So what payoff do I get from this? What payoff do I get from this? Okay, I get 3 in the first period, just as I did from my original defection. Right, that's good news. But now in the second period, discounted, I actually get -1. Right? I'm actually doing even worse in the second period because I'm cooperating while Jake's defecting. And then the third period, I get 0, and in the fourth period, I get 0, and so on. All right, so the total payoff to this defection is 3 minus delta. All right? Now that's even worse than the defection we considered to start with. The defection we considered to start with, I got 3 in the first period, and thereafter I got 0. Now I got 3 in the first period, -1 in the second period, and then 0 thereafter. Right? So this defection in which I defect, this move away from equilibrium, in which I cheat in the first period, and then don't go along with the punishment, I don't in fact play D forever, is even worse. Is that right? It's even worse. Right? So what's the lesson here? The lesson here is the reason that I'm prepared to go along with my own punishment and play D forever after a defection is what? It's if Jake is going to play D forever, I may as well play D forever. Is that right? So another way of saying this is the only way in which I could possibly hope to have a profitable deviation, given that Jake's going to revert to playing D forever, is for me to defect on Jake once and then go along with playing D forever. Right? There's no point, once he's playing D, there's no point in me doing anything else. All right? So this is worse. This is even worse. This defection is even worse. And more generally, the reason this is even worse is because the punishment we looked at before, which was DD forever, the punishment DD forever, here it is, right, the punishment DD forever is itself an equilibrium. It's credible because it's itself an equilibrium. All right, so unlike in the finite repeated games we looked at last time, unlike in the 2-period or the 5-period repeated games, here the punishment really is a credible punishment because what I'm doing in the punishment phase is playing an equilibrium. Right? There's no point considering any other deviation other than deviating, other than playing D once and then just going on playing D. All right? So that's one other possible deviation, but there are others you might want to consider. So far, all we've considered is what? We considered the deviation where in the very first period, I cheat on Jake, and then I just play D forever. But what about the second period? Right? Another thing I could do is, how about cheating not in the first period, not in the first period of the game, but in the second. All right, so according to this strategy, what I'm going to do, the first period of the game, I'll go along with Jake and cooperate, but in the second period, I'll cheat on him. All right? Now, how am I going to check whether that's a good deviation or not? How do I know that's not going to be a good deviation? Well, we already know that I'm not going to want to cheat in the first period of the game. I want to argue that exactly the same analysis tells me I'm not going to want to cheat in the second period of the game. Why? Because once we reach the second period of the game, it is the first period of the game. Right? Once we reach the second period of the game, looking from period 2 onwards is exactly the same as it was when we looked from period 1 initially. So say again, what we argued before was, on the board I've now covered up, what we argued before was, no, actually it's here. What we argued before was, I'm not going to want to cheat in the very first period of the game, provided delta's greater than a third. And I want to claim that same argument tells me I'm not going to want to cheat in the second period of the game, provided delta's bigger than a third, and I'm not going to want to cheat in the fifth period of the game, provided delta's bigger than a third. Right? Because this game from the 5th period on, or the 500th period on, or the 1000th period on, looks exactly the same as it does from the beginning. All right? So what's neat about this argument is the same analysis. The same analysis says this is not profitable. This is not profitable if delta is bigger than a third. All right? So what have we learned here? I want to do some nerdy lessons and then some actual sort of real-world lessons. So let's start with the nerdy lessons. The nerdy lesson is this Grimm strategy works because both, let's put it up again so we can actually see it. This Grimm strategy, here it is, it works because both the play that it suggests if we both cooperate and the play that it suggests if we both defect are themselves equilibria. These are credible threats and credible promises because what you end up doing both in the promise and in the threat is itself equilibrium behavior. All right, that's good. All right. The second thing we've learned, however, is for this to work, we need delta to be bigger than a third. We need the probability of continuation to be bigger than a third. All right, so leaving aside the nerdy stuff for a second, you'll have more practice on the nerdy stuff on the homework assignment. The lesson is we can get cooperation in the prisoner's dilemma using the Grimm trigger. Right? Remember, the Grimm trigger strategy is cooperate until someone defects and then defect forever. Right? So we get cooperation in the prisoner's dilemma using the Grimm trigger as a subgame perfect equilibrium. Right? So this is an equilibrium strategy. That's good news. Right? Provided the probability of continuation is bigger than a third. All right? Let's try and generalize that lesson away from the prisoner's dilemma. All right, so last time our lesson was about what in general could we hope for in ongoing relationships. All right, so let's put down a more general lesson that refines what we learned last time. All right, so the more general lesson is, let me do it here, in an ongoing relationship, let me mimic exactly the words I used last time. So for an ongoing relationship, to provide incentives for good behavior today, it helps. Right, what we wrote last time was it helps for that relationship to have a future. That's what we wrote last time. But now we can refine this. It helps for there to be a high probability that the relationship will continue. All right, so the specific lesson for prisoner's dilemma and the Grimm-Traeger strategy is we need delta, the probability of continuation, to be bigger than a third. But the more general intuition is, if we want my ongoing business relationship with me and Jake to generate good behavior, so I'm going to provide him with good fruit and he's going to provide with good vegetables, we need the probability that that relationship will continue to be reasonably high. And I claim this is a very natural intuition. Why? Because the probability that the relationship will continue is the weight that you put on the future. Right? The probability that the relationship will continue, this is the weight you put on the future. The more weight I put on the future, the more likely, the easier it is for the future to give me incentives to behave well today. The easier it is for those to overcome the temptations to cheat today. Right, that seems like a much more general lesson than just the prisoner's dilemma example. All right, let's try to push this to some examples and see if it rings true. Right, so the lesson we've got here is, to get cooperation in these relationships, we need there to be a high probability, a reasonably high probability that they're going to continue. We know exactly what that is for prisoner's dilemma, but the lesson seems more general. So here's two examples. How many of you are seniors? One or two, quite a few of you are seniors. Keep your hands up a second. Of those of you who are seniors, we can pan these guys. Let's have a look at them. All right. Actually, why don't we get all the seniors stand up? Get you to work a bit here. All right, now the tricky question, the tricky personal question. How many of you who are seniors are currently involved in have a significant other? Stay standing up if you have a significant other. Look at this, it's pathetic. What have I been saying about economic majors? All right, so let's just think about, so stay standing a second. Let's get these guys to think about it in a second. All right, so seniors who are involved in ongoing relationships with significant others, what do we have to worry about those seniors? Well, these seniors are about to depart from the beautiful confines of New Haven, and they're going to take jobs in different parts of the world. And the problem is, some of them are going to take jobs in New York, while their significant other takes a job in San Francisco or Baghdad. Or whatever, let's hope not Baghdad, but London, shall we say. All right? Now, if it's the case that you are going to take a job in New York next year and your significant other is going to take a job in Baghdad or London, or anyway, far away, what does that do to the, in reality, being cynical a little bit, what does that do to the probability that your relationship's going to last? It makes it go down, right? It makes it go down. It lowers the probability that your relationship's going to continue, right? So what is the prediction? Let's be mean here. How many of you have, these are the people with significant others who are seniors, how many of you are going to be separated by a long distance from your significant others next period? Oh, one of them at the back, okay? One guy, no, two, there we go, sort of honesty here. 3, 4 of them, right? So what's our prediction here? What does this model predict as a social science experiment? What does it predict? It predicts that for those of you who just raised your hands, those seniors who just raised their hands, who are about to be separated by large distances, those relationships, each player in that relationship is going to have a lower value on the future. So during the rest of your senior year, right, during the spring of your senior year, what's the prediction of this model? They're going to cheat. All right? All right? All right? So we can actually do a controlled experiment. What we should do here is we should keep track of the people here, the seniors who are about to have long-term relationships, right, who are going to be separated. You can sit down now, I'm sorry to embarrass you all, right? We could keep track of those seniors who are about to be separated and go into long-distance relationship, and those that are not, the people who are not are our control group, and we should see if during the spring semester the people who are going to be separated cheat more often than the others. All right? All right? So it's a very clear prediction of the model that's relevant to some of your lives. All right? Let me give you another example that's less exciting perhaps, but same kind of thing. Consider the relationship that I have with my garage mechanic. I should stress this is not a significant other relationship. All right? So I have a garage mechanic in New Haven, all right? And that garage mechanic fixes my car. And we have an ongoing business relationship. He knows that whenever my car needs fixing, even if it's just a small thing like an oil change, I'm going to go to him and have him fix it, even though it might be cheaper for me to go to Jiffy Lube or something. All right, so I'm going to take my car to him to be fixed, and he's going to make some money off me on even the easy things. All right, what do I want in return for that? I want him to be honest, and if all I need is an oil change, I want him to tell me that, and if what I actually need is a new engine, he tells me I need a new engine. All right, so my cooperating with him is always going to him, even if it's something simple, and his cooperating with me is his not cheating on fixing the car. He knows more about the car than I do. All right? But now what happens if he knows either that I'm about to leave town, which is the example we just did, or more realistically, he kind of knows that my car's a lemon and I'm about to get rid of it anyway. Once I get a new car, I'm not going to go to him anymore because I have to go to the dealer, right, to keep the warranty intact. So if he knows that my car is about to break down anyway, and he knows that I know the car's about to break down anyway, and my lemon of a car is about to be passed on probably to one of my graduate students, then, sorry, but it's pretty, all right, then what's going to happen? What's going to happen? So I'm going to have an incentive to cheat because I'm going to start taking my useless car to Jiffy Lube for the oil changes, and he's going to have an incentive to cheat. He's going to start telling me, you know, you really need a new engine or a new clutch. It's a manual, so I have a clutch. All right, it's a real car, right? So I'm going to need a new clutch rather than just tightening up a bolt. All right. So once again, the probability of the continuation of the relationship as it changes, it leads to incentives to cheat. Right? It needs that relationship breaking down. All right? That's the content. That's the real world content of the math we just did. All right. Let's try and push this a little further. Now, what we've shown is that the Grimm trigger works provided delta's bigger than a third, and delta being bigger than a third doesn't seem like a very large continuation probability. All right? Right, so just having a probability of a third that the relationship continues allows the Grimm trigger to work. So that seems good news for the Grimm trigger. However, in reality, in the real world, the Grimm trigger might have some disadvantages. So let's just think about what the Grimm trigger is telling us in the real world. It's telling us that if even one of us cheats just a little bit, right, I just provide one item of rotten fruit to Jake, or he gives me one too few branches of asparagus in his provisions to me, then we never do business with each other again ever. Right? It's completely the end. We just never cooperate again. Right? And that seems a little bit drastic. It's a little bit draconian, if you like. Right? Right? So in particular, in the real world, there's a complication here. In the real world, every now and then, one of us is going to cheat by accident. I'm just not, you know, that day I didn't have my glasses on and I put in a rotten apple in the apples I supplied to Jake. And in the fruit, you know, he was counting out the asparagus and he just, you know, he lost count at 1,405 and he gave me one too few. All right? And so we might want to worry about the fact that the Grimm trigger, it's triggered by any amount of cheating and it's very drastic. It says we never do business again. All right? The Grimm trigger is the analog of the death penalty. It's the business analog of the death penalty. It's not that I'm going to kill Jake if he gives me one too few branches of asparagus, but I'm going to kill the relationship. right? For you seniors or otherwise who are involved in personal relationships, it's the equivalent of saying if you even see your partner looking at someone else and alone sitting next to them in class, the relationship's over, right? It seems drastic, all right? So we might be interested, because mistakes happen, because misperceptions happen, we might be interested in using punishments that are less draconian than the grim trigger, less draconian than the death penalty. Is that right? All right. So what I want to do is I want to consider a different strategy, a strategy other than the grim trigger strategy, and see if that could work. All right. So where shall I start? Let's start here. All right. Okay, so again, what I'm going to revert to is the math and the nerdiness of our analysis of the prisoner's dilemma, but I want you to have in mind business relationships, your own personal relationships, your friendships, and so on. Everything, more or less everything you do in life involves repeated interaction. So have that in the back of your mind, but let's be nerdy now. All right? So what I want to consider is a one-period punishment. A one-period punishment. All right? So how are we going to write down a strategy that has cooperation but a one-period punishment? So here's the strategy. It says, it's kind of a weird thing, but it works. Play C to start. Play C to start. And then play C if, here's the tricky thing, it's going to seem weird, but trust me for a second. Play C if either CC or DD were played last. Right? So if in the previous period either both people cooperated or both people defected, then we'll play cooperation this period. All right? And play D otherwise. Play D if either CD or DC were played last. All right, let's think about this strategy for a second. What does this strategy mean? So provided people start off cooperating and they go on cooperating, if both Jake and I play this strategy, in fact we'll cooperate forever. Is that right? Right? So I claim this is a one-period punishment strategy. So let's just see how that works. So suppose Jake and I are playing this strategy. We're supposed to play C every period. And suppose, deliberately or otherwise, I play D. All right? So now, in that period in which I played D, the strategies played were D by me and C by Jake. All right? So next period, what does this strategy tell us both to play? Right, so it was D by me and C by Jake. So this strategy tells us to play D. All right, so next period, both of us will play D. All right, so both of us will be uncooperative for precisely for that period, that next period. Now what about the period after that? The period after that, Jake will have played D, I will have played D, so this is what will have happened. We both played D, and now it tells us to cooperate again. Okay, everyone happy with that? Right, so this strategy I've written down, it seems kind of cumbersome, but what it actually induces is exactly a one-period punishment. If Jake cheats, if Jake is the only cheat, then we both defect for one period and go back to cooperation. If I'm the only person who cheats, then we both defect for one period and go back to cooperation. It's a one-period punishment strategy. And of course the question you should be asking is this going to work? Is this an equilibrium? All right, so let's just check. Is this an SPE? Is it an equilibrium? All right, so what do we need to check? We need to check, as usual, that the temptation is less than or equal to the value of the promise, the value of the promise of continuing incorporation, the value of the promise, minus the value of the threat. All right, and once again, we have to be careful because the temptation occurs today, and this difference between values occurs tomorrow. Is that right? So this isn't anything new. This is what we've always written down. This is what we have to check. All right, so the temptation for me to cheat today, that's the same as it was before. It's 3 minus 2. All right? The fact it's tomorrow is going to give me a delta here. All right? Here's our square bracket. So what's the value of the promise? So provided we both go on cooperating, we're going to go on cooperating forever, in which case we're going to get 2 forever. Is that right? So this is going to be the value of 2 forever starting tomorrow. And again, forever means until the game ends. And the value of the threat is what? Be a bit careful now. It's the value of, all right, so what's going to happen? If I cheat, then tomorrow we're both going to cheat. Right? Tomorrow we're both going to cheat. Right? So tomorrow, what am I going to get tomorrow? 0. All right? So it's the value of 0 tomorrow, and then 2. Oh, sorry. We're both going to cheat. We're both going to play D, and then the next period, what's going to happen? We're going to play C again, right? And from there on, we're going to go on playing C. All right, so it's going to be the value of 0 tomorrow, and then 2 forever, starting the next day. All right, that's what we have to evaluate. All right, so 3 minus 2, I can do that one again, that's 1. All right, so what's the value of 2 forever? Well, we did that already today. What was it? It's in your notes. Actually, it's on the board. It's the X up there. What is it? Here it is. 2 forever. We figured out the value of it before, and it was 2 over 1 minus delta. All right, so the value of 2 forever is going to be 2 over 1 minus delta. All right. How about the value of 0? So starting from tomorrow, I'm going to get 0, and then with 1 period delay, I'm going to get 2 forever. All right, well, 2 forever, we know what the value of that is. It's 2 over 1 minus delta. But now I get it with 1 period delay. So what do I have to multiply it by? By delta. Good. So the value of 0 tomorrow and then 2 forever starting the next day is delta times 2 over 1 minus delta. And here's the delta coming from here, which just takes into account that all this analysis is starting tomorrow. All right, so to summarize, this is my temptation today. This is what I'll get starting tomorrow if I'm a good boy and cooperate. And this is the value of what I'll get if I cheat today. Starting tomorrow, I'll get nothing, and then I'll revert back to cooperation. And since all of these values in this square bracket start tomorrow, I've discounted them by delta. All right, now this requires some math. So bear with me while I probably get some algebra wrong, and please, can I get the TAs to stare at me a second, because I'll probably get this wrong. Okay, so what I'm going to do is, I'm going to look at my notes. I'm going to cheat. That's what I'm going to do. Okay, so what I'm going to do is I'm going to have 1 is less than or equal to. I'm going to take out a common factor of 2 over 1 minus delta and delta. So I'm going to have 2 delta over 1 minus delta. And that's going to leave inside the square brackets. This is a 1, and this is a delta. All right, so this delta here was that delta there, and then I took out a common factor of 2 over 1 minus delta from this bracket. Everyone okay with the algebra? Just algebra, nothing fancy going on there. All right, so that's good because now the 1 minus delta cancels, right? This cancels with this. So this tells us we're okay provided provided a half is less than or equal to delta. and we're done. All right? Okay, so don't worry too much about the algebra. Trust me on the algebra a second. All right, let's just worry about the conclusion. What's the conclusion? The conclusion is that this one-period punishment is an SPE. It will be enough. One period of punishment will be enough to sustain cooperation in my prisoner's dilemma repeated business relationship with Jake, or in the seniors' relationships with their significant others, provided delta is bigger than a half. What did delta need to be for the Grimm strategy? A third. All right, so what do we learn here? What did we learn? We learned, so noodly what we learned was that for the Grimm strategy, we needed delta bigger than a third. For the one period punishment, we needed delta to be bigger than a half. But what's the more general lesson? The more general lesson is, if you use a softer punishment, a less draconian punishment, for that to work, we're going to need a higher delta. Is that right? Is that right? So what we're learning here is there's a trade-off. There's a trade-off in incentives. And the trade-off is, if you use a shorter punishment, a less draconian punishment, instead of cutting people's hands off or killing them or never dealing with them again, you just don't deal with them for one period. That's okay, provided there's a slightly higher probability of the relationship continuing. So shorter punishments are okay, but they need, well, I don't know, the implication sign isn't really necessary there. They need more value, or more weight delta on the future. All right? Now I claim that's very intuitive. That's very intuitive. What it's saying is we're always trading things off in the incentives. We're trading off the ability to cheat and get some cookies today versus waiting and we hope getting cookies tomorrow. Right? All right? So if in fact the reward, or the difference between the reward and the punishment, isn't such a big deal, isn't so big, and the punishment is just I'm going to give you one fewer cookies tomorrow, right? Then you better be pretty patient not to go for the cookies today. All right? I was about to say those of you who have children, I'm probably the only person in the room with children, that cookie example will resonate. For the rest of you, wait until you get there, you'll discover that in fact cookies are the right example. All right? So shorter punishments, less draconian punishments, less reduction in your kid's cookie ration tomorrow is only going to work, only going to sustain good behavior, provided those kids put a high weight on tomorrow. In that case, it isn't that the kids are worried about the relationship breaking down. I mean, you're stuck with your kids. It's just that they're impatient. All right? All right. Okay, so we've been doing a lot of formal stuff here, and I want to go on doing formal stuff, but what I want to do now is spend the rest of today looking at an application. All right? An application that's, I hope, going to convince you that repeated interaction really matters. Okay? So this is assuming that the one about the seniors and their boyfriends and girlfriends wasn't enough. Okay. So the application is going to take us back a little bit, because what I want to talk about is repeated moral hazard. And moral hazard is something we discussed the first class after the midterm. All right? So what I want to imagine is that you are running a business in the US and you are considering making an investment in an emerging market. And again, so as not to offend anybody who watches this on the video, let's just call that emerging market Fredonia, right? Rather than give it a name like Kazakhstan. Oh, no, I shouldn't have done that. Like a name like something other than Fredonia. All right? All right? All right? So Fredonia, for those who don't know, is a republic in a Marx Brothers film. All right? So you're thinking of outsourcing some production of part of what your business is to Fredonia. And the reason you're thinking of doing this outsourcing, what makes it attractive, is that wages are low in Fredonia. So you get this outsourced in Fredonia, you think you're going to get it done cheaply. All right? The downside is, because Fredonia is an emerging market, the court system is not well, it doesn't operate very well, and in particular, it's going to be pretty hard to enforce contracts and to jail people and so on in Fredonia. Right? So you're considering outsourcing. The plus is, from your point of view, the plus is wages are cheap where you're going to get this production done. The downside is it's going to be hard to enforce contracts, so this is an emerging market. All right? So what you're considering doing is employing an agent, and you're going to pay that agent W. Right? So W is the wage if you employ them. And I'll put this up in a tree in a second. Right? Let's assume that the going wage in Fredonia is 1. Right? We'll just normalize it. All right? So the going wage in Fredonia is 1. And let's assume that to get this outsourcing to work, you're going to have to send some resources to your agent, your employee in Fredonia, and let's assume that the amount you're going to have to send over there is equivalent to another 1. Right? So the going wage in Fredonia is 1, and the amount you're going to have to invest in giving this agent materials or machinery is another 1. All right? And let's assume that this project is a pretty profitable project. So if the project succeeds, if the project goes ahead and succeeds, it's going to generate a gross revenue of 4. Right? Of course, you have to invest 1, so that's a net revenue of 3 for you. Right? But nevertheless, there's a big potential return here. All right? The bad news is that your agent in Fredonia can cheat on you. In particular, what he can do is he can simply take the 1 that you've sent to him, right, sell those materials on the market, right, and then go away and just work in his normal job anyway. So he can get his normal wage of 1, just going and doing his normal job, whatever that was, and he can steal the resources from you. All right? So let's put this up as a kind of tree. This is a slight cheat, this tree, but we'll see why in a second. All right? So your decision is to invest and set W. Right? So if you invest in Fredonia, you'll invest and set W, set the wage you're going to pay him. Right? The going wage is 1, but you could set a different wage. All right? Or you could just not invest. If you don't invest, you get nothing, and your agent in Fredonia just gets the going wage of 1. All right? If you do invest in Fredonia and set a wage of W, then your agent has a choice. Either he can be honest, or he can cheat. If he cheats, what's going to happen to you? You had to invest 1 in sending it over there. You're going to get nothing back, so you'll get -1. All right? And he will go away and work his normal job and get 1, and in addition, he'll sell your materials. So he'll get a total of 1 plus 1 is 2. Thank you. Okay? He'll get a total of 2. All right? Right? On the other hand, if he's honest, then you're going to get a return of 4 minus the 1 you had to invest, minus whatever wage you paid to him. Right? So your return will be 3 minus the wage you pay him. Right? You're only going to pay him once the job's done. 3 minus W. And he's going to get W. He's done his job, he hasn't exercised his outside option, he hasn't sold your materials, so he'll just get W. Right? Now I'm slightly cheating here because this isn't really the way the tree looks, because I could choose different levels of W. So this upper branch where I invest and set W, there's actually a continuum of such branches, 1 for each possible W I could set. But for the purpose of today, this is enough. This gives us what we need to see. All right? So let's imagine that this is a one-shot investment. What I want to learn is in this one-shot investment, I invest in Fredonia, I hire my agent once. What I want to learn is how much do I have to pay that agent to actually get the job done? And remember the starting position. The starting position is it looks very attractive. It looks very attractive because the returns on this project are 4, or 4 minus 1, given the investment. So the surplus available on this project is 3 minus the wage, and the going wage was just 1. So it looks like there's lots of profit around to make this outsourcing profitable. I mumbled that, so we try it again. So the reason this looks attractive is the going wage is just 1, so if I just pay him 1 and he does the project, then I'll get a gross return of 4 minus the 1 I invested minus the 1 that I had to pay him for a net return of 2. seems like it's a 100% profitable project. Right? So it looks very attractive. What's the problem? The problem is, if I only set, this is going to be a backward induction, if I set the wage equal to the going wage, so if I set W equal to 1, what will my agent do? He's going to cheat. Right? The problem is, if I set W equal to 1, which is the going wage in Fredonia, the agent will cheat. And if he cheats, I just lose my investment. So how much do I have to set the W to? Let's look at this. All right, so we have to set W. What I need is I need his wage to be big enough so that being honest and going on with my project outweighs his incentive to cheat. I need W to be bigger than 2. Is that right? I need W to be at least as big as 2. All right? All right, so in setting the wage in equilibrium, what are we going to do? I'm going to set a wage, let's call it W star, equal to 2 plus a penny. Is that right? So this is an exercise which we visited the first day after the midterm. This is about incentive design. It's about incentive design. In this one-shot game, which we can easily solve by backward induction, I'm going to need to set a wage equal to 2, and then he'll work. All right, so in a minute we're going to look at the repeated version of this, but before we do, let's just sum up where we are so far. What is this telling us? It's telling us that when you invest in an emerging market where the courts don't work, so they're not going to be able to enforce this guy you're not going to be able to enforce this guy to work well, in particular he can run off with your investment, even though wages are low, so it seems very attractive to do outsourcing, if you worry about getting incentives right, you're going to have to pay an enormous wage premium to get the guy to work. Right? So the going wage in Fredonia was 1, but you had to set a wage equal to 2, a huge wage premium of 100% wage premium to get the guy to work. All right? So the wage premium in this emerging market is 100%. You're paying 2, even though the going wage is 1. And by the way, this is not an unreasonable prediction. If you look at the wages paid by European and American companies in some of these emerging markets, which have very, very low going wages, and look at the wages that are actually being paid by the companies that are doing outsourcing, you see enormous wage premium. It's enormous premium over and above the going wage. All right. Now what I want to do, I want to put that up there, and I want to revisit exactly the same situation. But now we're going to introduce the wrinkle of the day. What's the wrinkle of the day? The wrinkle of the day is you're not only going to invest in Fredonia today, but if things go well, you'll invest tomorrow. And if things go well again, you'll invest the day after, at least with some significant probability. Right? So the wage premium we just calculated was the one-shot wage premium. It was getting this job, this single one-shot job, outsourced to Fredonia. And now I want to consider how much you're going to have to pay, what a wage is going to be in Fredonia, in the foreign investment sector, if instead of just having a one-shot, one-job investment, you're investing for the long term. You're going to be in Fredonia for a while. All right? So consider repeated interaction with probability delta of continuing. So we don't know that you're going to go on in Fredonia. Things might break down in Fredonia because there's a coup. It might break down in Fredonia because the American administration says you're not allowed to do outsourcing anymore. All those things might happen, but with some probability delta, the relationship's going to continue. So repeated interaction with probability delta. All right? And let's redo the exercise we did before to see what wage you'll have to charge. All right? So what our question is, what wage, and let's call it W double star now. We call it previously double stars. Let's call it W double star. What wage will you pay? All right? And the way we're going to solve this is exactly using the methods we've learned in this class. So what we're going to compare is the temptation to cheat today. And we better make sure that that's less than delta times the value of continuing, well, the relationship minus the value of ending the relationship. Let's call this tomorrow. All right, so what's happening now is, once again, I'm employing my agent in Fredonia, and provided he does a good job, I'll employ him again tomorrow, at least with probability delta. Right? But if he doesn't do a good job, if he runs off with my investment and doesn't do my job, what am I going to do? Well, what would you do? You'd fire him, right? You'd fire him. Is that right? Right? So the punishment, it's clear what the punishment's going to be here. The punishment is, if he doesn't do a good job, you fire him. Right? The value of ending the relationship, this is firing. Firing, and this is continuing. All right? All right, so let's just work out what these things are. So his temptation to cheat today. If he cheats today, he doesn't get my wage. All right? But he does run off my cash, and he does go and do his job at the going wage. So if he cheats today, he gets 2, he's stolen my cash, and he's going off and working at the going wage, but he doesn't get what I would have paid him, W double star, right, if the job was well done. All right? We need this to be less than the value of continuing the relationship. Well, let's do the easy bit first. What does he get if we end the relationship? What does he get if we end the relationship? He's been fired, so he'll just work at the going wage forever, right? Right. So this is the value. This is the value of 1 forever, or at least until the end of the world. All right. And this is the value of what? As long as he stayed employed by me, what's he going to get paid every period? What's he going to get paid? W double star, right? So the value of W double star forever. All right? Let me cheat a little bit and assume that the probability the probability of some coup happening that ends our relationship exogenously is the same probability of the coup happening and ending his ongoing wage endogenously. So we can use the same delta. All right. So let's do some math here. What's the value of W double star forever? So remember, the value of 2 forever was what? 2 over 1 minus delta. So what's the value of W double star forever? W double star over. Okay. So this is going to be W double star over 1 minus delta. And what's the value of 1 forever? 1 over 1 minus delta. The whole thing is multiplied by delta. And this is 2 minus W double star. All right, now I need to do some algebra to solve for W double star. I can't even say it. All right, so let's try and do that. So I claim that this is the same as 1 minus delta 2 minus 1 minus delta W double star is less than W double star delta minus delta times 1. Everyone okay with that? And one more line. Let me just sort out some terms here. So taking things on the other side, I have 1 minus... I hope that's right. That seems right. Just checking my algebra a second. All right, so 1 minus delta 2 plus delta 1 has to be less than or equal to W double star delta plus 1 minus delta W double star, which is equal to W double star. Okay, so someone should just check my algebra at home, but I think that's right. All right, so the last two steps were just algebra, nothing fancy. What have we learnt? We've learnt that the wage I have to pay this guy, the wage I have to pay him, lies somewhere between 2 and 1. All right, lies somewhere between 2 and 1, but we can do a bit better than that. Let's just delete everything here. So in particular, if delta is equal to 0, what's W double star, right? If delta is equal to 0, W double star is equal to what? Somebody? Equals to 2, right? Equal to 2, right? And that's what we had before. In the one-shot game, there it is up there, where there was no possibility of continuing the relationship tomorrow, I had to pay him a wage of 2, or if you like, a wage premium of 100%. If there's no probability, if there's no chance of continuing this relationship, if delta is equal to 0, we find again that I'm paying 100% wage premium. Let's take the other extreme. If delta is equal to 1, so I just know this relationship is going to continue. Right? If delta is equal to 1, so there's no probability of the world ending or there being a coup, then what's W double star? It's equal to 1. What's that? What's 1? It's the going wage, right? It's the going wage. Right? So this is the going wage. If I know for sure we're going to continue forever, I can get away with paying the guy the going wage, at least in the limit. Right? If I know we're not going to, if we know we're not going to continue, then I have to play the one-shot wage. But let's look at a more interesting intermediate case. Suppose delta is equal to a half. There's just a half probability. It's pretty low. There's a half probability that your company, American Widgets, right, is going to stay in Fredonia. With probably a half it's going to be done next period. Probably a half it's going to stay. What does that do to the wage? What happens to the wage in this case in which there's probably about half of American Widgets staying in Fredonia? Right, it's a half between 2 and 1, which is therefore 1.5. Or another way of saying that is the wage premium is now only 50%. What have we learned from this example? It's just an example of using repeated games. Well, the first thing we've learned is it's kind of easy to get used, once we get used to it, it's easy to use this technology of comparing temptations to cheat with values of continuing the relationship versus values of continuing in a cooperative relationship versus the value of the punishment, which in this case was just firing the guy. Right? But more specifically in this example, we've learned that even a relatively small probability of this relationship continuing, right, so this is good news for those of you who are seniors and about to move to San Francisco while your significant other is going to London, even a small probability of the relationship continuing drastically reduces the wage premium. The amount you have to pay your significant other not to cheat on you as they go off to London or San Francisco is drastically lower if there's some probability, in this case just a half, of continuing. All right? Before you leave us, one more thought, okay? So how does this all work? Let's summarize. To get good behavior in these continuing relationships, there has to be some reward tomorrow. Right? That reward needs to be higher if the weight you put on tomorrow, if the probability of continuing tomorrow is lower. Right? The less likely tomorrow is to occur, the bigger the reward has to be tomorrow. We're going to have to charge wage premia to employ people in Fredonia, but those premia will come down once we realize that we're in established relationships in Fredonia, once American firms are established and not fly-by-night operations in Fredonia. All right? Whether that's good news or bad news for Fredonia, we'll leave there. On Monday,